Hello, hi, welcome back to the second part of raindrop erosion. So in this part, we will learn on transportation distance of soil particles in splash erosion, raindrop size, we will calculate terminal velocity of raindrops, and finally we have some exercise. Okay, so the focus of this second part is on the terminal velocity. So anyway, we will start with transportation distance of soil particles. So this is the formula to calculate the distance of soil particles in splash erosion, how far the soil can travel. So according to this formula, 4 times k is coefficient of resistance multiplied by velocity of falling raindrops, and this is to the power of 2, and you divide by gravity acceleration and then multiply this part with sine alpha. So sine alpha is angle of slope or angle of deviation of direction of the falling drop from the vertical. Okay, so don't worry about this formula because it's very simple and information will be given. Okay, so now we look at raindrop size. So raindrop size can be determined using one, size of splash, secondly by absorbent paper with light dust, and thirdly by flour palette method. Okay, so using flour palette method, the raindrops are catch in a dish containing flour. So this method was introduced by Hudson long time ago in 1964. So this is a graph which was generated from this experiment, flour palette method. So this is the palette mass, and this is the mass of raindrop, and this is a calibration curve. So this is only for your information. Don't worry because we are not going to do this experiment in this course, but it's good if you know about this. Okay, so now we are going into the most interesting part of this lecture, which is terminal velocity. So following Smith, this is the equation for calculating velocity. So R in this equation is radius of raindrop in millimeter. So Vk is terminal velocity of raindrops in meter per second. Okay, after that, following another scientist, Lastikin, 1964, the equation is simplified and it becomes like this. Very simple. Okay, so D is drop diameter of raindrop. Okay. So there is also a relationship between terminal velocity and raindrop size. So as the raindrop size goes higher, the terminal velocity also goes higher. So for example, if you have a raindrop with 5 millimeter size, the impact velocity will be about 9 meter per second. So, okay. So the values of terminal velocity for different sizes of water droplets in stagnant air is also shown in this table. So if you have drop diameter 0.01, then the terminal velocity will be 27 centimeter per second. And as the drop diameter goes higher, the terminal velocity will be higher. So this drop diameter is only until 0.58. Okay. What happens if you have a higher drop diameter? So if you have a higher drop diameter, perhaps you can use this equation. Yeah? Okay. Okay, now we want to see what is terminal velocity. Okay, terminal velocity happen. Okay, terminal velocity is the fastest speed of an object can travel at when it has resistive force acting on it with constant velocity. So when an object falls, initially the only force acting on it is gravity. It's like this. So this is mg. Also the weight. So as it starts to move, air resistance acts on it. So this is when it starts to move, air resistance acts on it, which is drag force. So Fd will increase in time, and resulting force, which is buoyancy force, Fb decrease. So from this one, you see there is buoyancy force. It's also decreasing as drag force increase. Okay, so when drag force is equal to weight minus Fb, buoyancy force, this is when the terminal velocity will occur. Okay, I hope from these two figures, it will help you to understand what is terminal velocity. Okay, so another way to remember terminal velocity is when you know that the velocity is constant. So the acceleration is 0. Okay? Okay. So this is how we derive a formula for terminal velocity of raindrops. So we have gravity force due to weight of raindrop. We have buoyancy force due to displacement of air by the raindrop. And we also have drag force due to friction between the raindrop and the surrounding air. This is what I already explained to you from the previous slide. Okay. Let D equals to drop diameter of rain. Therefore, volume of raindrop is equals to pi over 6 d to the power of 3. Okay, so from this formula of volume of raindrop, force of gravity is equals to this equation, and force of buoyancy is equals to this equation, and this is density of water and density of air. And finally, we have drag force, which is according to this formula. So this CD is coefficient of drag. This is given in table 3.4. So for the rest, we have area, and this is terminal velocity. So, okay, before we see how can we calculate terminal velocity using these formulas, we move to the next slide. Okay, this slide shows the relationship between drop diameter and drag coefficient. So with 0.2 drop diameter, the drag coefficient is 4.2. But as the drop diameter goes higher, for example like this, 5 millimeter, the drag coefficient will be slower. Yeah. Okay, so this is according to Mason 1957. So it's an old literature. Okay, so terminal velocity occurs when Fd is equals to Fg minus Fb. So this is the formula for calculating drag force. And this is the formula for calculating gravity force. And this is the formula for calculating buoyancy force. Okay, by solving this equation, you are interested to find this V, because this V is terminal velocity. So finally, after solving this equation, you will get this formula. Vt is equals to this equation. So, because we want to find terminal velocity. So why are we interested to find terminal velocity? As we have learned from the first part of raindrop erosion, terminal velocity is used to calculate the energy, the kinetic energy. Okay, so that's why calculating terminal velocity is important. So now we have come to the last part of this lecture where you have to do an exercise. Actually, you have to do 2 exercises. So don't forget to submit this exercise before 17 March 5 p.m. Okay, let's read the question together. So you have to determine the terminal velocity and kinetic energy of 2 mm and 4 mm diameter raindrops if drag coefficient is this value 0.5 for 2 mm drop or and 0.559 for 4 mm drop. So the drag coefficient is given and also density of water and air also given. So you just have to use the equation to find terminal velocity and kinetic velocity. So I put some clues here. First, you find Vt for 2 mm and 4 mm, and this is the answer. So you can check your answer here. And secondly, you find mass of raindrop. Okay, mass of raindrop is equals to volume of drop times water density. So the answer should be this too. And finally, you find kinetic energy. And the answer is 4.3 to the power of negative 3 kilogram square meter per square second. Okay. Okay, but if you have any question, you can always WhatsApp me and ask me. Okay, so next, the second question is, this is quite simple. Calculate terminal velocity of a raindrop of 0.8 millimeter diameter at standard atmospheric pressure and air temperature of 20 degrees Celsius. So you can use the same information as in the previous question. Okay, but you take air density as 1.2 kilogram per cubic meter. So the answer should be around this value, 3.265. So I hope you understand all these, all the points in this topic. And if you have any question, don't forget, you can ask me anytime. And don't forget to submit your exercise. Okay, see you again in the next lecture. Bye.